Hey guys, it's right after fifth period. Gonna try to record a bunch of these videos. So today is my video over the recommended section for the Tuesday Owls. That's sections 9, 10, and 15. So we'll start with one from section 9, the pOH of an aqueous solution of 0.465 molar phenol, which is a weak acid, is blank. So let's get started by writing an equilibrium expression for this weak acid. So we have an acid which exists already in solution. So we have C6H5OH plus water, and that's going to form an equilibrium expression. And since it tells us it's an acid, that means it's going to donate one of its H's. So it's going to look like this. And H2O is going to act as a base, and it's going to accept one and become the conjugate acid H3O+. So let's make an ice chart for this now, since it's a weak acid. Our initial concentration of phenol is 0.465 molar, and we have none of the conjugates there. So that means we're going to minus X plus X plus X, and so our final answer, or our final equilibrium, would be found with 0.465 minus X, X, and X. Now, the minus X here is going to be pretty insignificant because of the 5% rule, so I'm just going to call that 0.465. Now, I'm going to go into my Ka values listed on the Owls here and find that the Ka of phenol is listed at 1.0 times 10 to the negative 10th. And so I'll set that equal to the concentration of my products times one another, so over the concentration of my reactants, C6H5OH, which is phenol. If I plug in my equilibrium values here, I get that those equal X squared over 0.465. So 1.0 times 10 to the negative 10th equals 0.465 under X squared. What that means is that X, if I do some algebra, which is equal to my concentration of hydronium, is going to be equal to 6.82 times 10 to the negative 6th. So if I take the negative log of 6.82 times 10 to the negative 6th, that gives me my pH, which is 5.17. But I'm not asked for pH, I'm asked for pOH. So 14 minus 5.17 equals my pOH, which equals 8.83. Hopefully, section 9 is a pretty straightforward one for y'all. The next section has to do with percent ionization. We're told that in a laboratory, a student measures the percent ionization of a 0.353 molar solution of formic acid to be 2.34%. Calculate the Ka values from this experimental data. Okay, so for this, we need to know our percent ionization formula, which is that percent ionized is equal to the moles of acid that dissociate over the initial molarity of our acid. So that little sub 0 means the initial times 100% to get us into a percent form. So let's start plugging in values. Our percent ionization is 2.34. So 2.34 is going to be equal to our moles of acid that dissociated, which is kind of what I'm trying to figure out, that X concentration, over my initial concentration of acid, which is 0.353 times 100. Now, I have to be kind of careful with my algebra here because of this times 100. So after I'm a little bit careful here, let me make sure that's a times sign rather than an x to avoid confusion. After a little bit of algebra and manipulation, I should see that x is equal to 8.26 times 10 to the negative third. What I want to do here is set up a ice chart for what my formic acid dissociating looks like. So I have formic acid interacting with water, which is going to find equilibrium as, oh, one too many O's there. Just going to find equilibrium like this. I set up my ice chart. I have some initial value, 0.35300. I have my changes, minus x, plus x, plus x. And I have my final values. Now, interestingly, I've already calculated x. I've already calculated how many moles of my acid are going to dissociate. So I can plug that in for both of these values, meaning my equilibrium value of x is 8.26 times 10 to the negative third. And that's true here too. And then over here, since I know my x, I'm not going to ignore it. If you know your x, you shouldn't ignore it. You shouldn't assume that it's negligible. And I'm going to plug that in there. Let me make all this stuff smaller so I have a little bit more room to work with here. So that was my initial work to figure out what my kind of equilibrium expression is going to be. So I'm tasked to find Ka. So Ka is what I'm looking for. And I know that Ka is going to equal 8.26 times 10 to the negative third squared, because that's the concentration of both my conjugate acid and my conjugate base, divided by the initial concentration of my acid, which is going to, or the initial equilibrium concentration, that is, which is 0.353 molar minus 8.26 times 10 to the negative third. And when I plug all that into my calculator, I get that I have a Ka value of 1.98 times 10 to the negative fourth for formic acid. So that's how we could calculate Ka from percent ionization. We'll do another one with those just because we don't do a lot of percent ionization in class. So let's do another one here that's slightly different. This time we're tasked with calculating the percent ionization from molarity. So if we remember our formula, percent ionization is equal to our moles dissociated over our initial concentration of acid times 100. So this time we're calculating percent ionization, and we already have a Ka value for hypochlorous acid, which is 3.5 times 10 to the negative eighth. We already have some other information about us, so let's see how far we can get. We're going to first write what's probably a good place to always start with a dissociation equation here. We make our ice chart. We have our initial concentration at 0.381, 0, and 0. We know that we'll minus x plus x plus x. So we know that this will be x, x, and 0.381. This time, since I don't know x, I'm just going to call it 0.381. Since I have a Ka value, I know that 3.5 times 10 to the negative eighth is equal to x squared over 0.381. So I know that x is equal to 1.15 times 10 to the negative fourth. Now, what is x really? X is my concentration of both of my conjugates but it is also equal to the concentration change in HClO, hypochlorous acid. So now that I've done that, I can plug this value, my change, up here into my change in moles dissociated. How much molar did I dissociate? And so I am left with my percent equals my X value that I calculated, 1.15 times 10 to the negative fourth, over my initial value, 0.381, times 100%, and that's going to equal 0.0303%. A pretty small value, a pretty low percent ionization. That makes sense because our Ka is very small. Moving on from section 10, we'll do one from section 15 where we're calculating pH or POH or OH minus, whatever. In this case, the hydroxide ion concentration of a weak base. So we have our weak base, methylamine, which has the formula CH3NH2. So what we want to do here is go ahead and write a dissociation equation. CH3NH2, which is not an ionic solid, mixed with water, is just going to simply accept another proton, and water will have donated, leaving it as hydroxide. We then set up our ice chart with our initial concentrations. We write in the change, minus X plus X plus X. And we come to terms with our equilibrium value. Again, I'm cool with just 0.465 because I don't know the value of X. I have my Kb, which is equal to 4.2 times 10 to the negative fourth. So I can say that equals X squared over 0.465. That means X is going to be equal to my concentration of hydroxide ion, which is equal to 1.40 times 10 to the negative 2. Now, it just asked me for hydroxide ion concentration, so I'm not going to go any further, but from here, I could find POH, I could use that to find pH, I could use that to find concentration of H+, but I'm just going to stop with where my answer is. So this is the most recent AL section that covers 9, 10, and 15. Hopefully that helps, and you can look back at these for your review. Thanks.